Let's identify the integral of the given function f of z equal to z around a circle centered at 2 plus I with radius r. So the path here is a circular path, but the center is no longer at the origin. Hence, we'll be using another form of parameterization specific to this path. Take note that our task here is to identify the integral of f of z dz along the given path. In this case, again, it's a circular path centered at 2 plus I, not the origin, with a specific radius. Still, this is equivalent to f of z of t times z prime of t dt from a to b. So we are to solve first, or to provide first, our z of t. We know already that this is not centered at the origin. So it's a circular path still. So we know that this the parametric for that is actually identified as z sub 0 plus r e to the power of I t. Our z sub 0 here is obviously identified as this. That's the center. And our r is actually equal to 3. So if we are going to simplify that further, this is the general form, but since we have here the specific values, our z sub 0 is 2 plus I plus your r is 3 e to the power of I t. That is the z of t we're going to use here. Okay? Now, with that idea, we can now show the z prime of t, or a derivative of that with respect to t. Again, with respect to t. So all other, all the rest of the values of, let's say, our terms without t will be treated as constant. So 2 becomes 0, I becomes 0, and you have here plus 3. Let me put it down because I don't have much space. So plus 3, then e to the u is e to the u and du, meaning the derivative of its exponent with respect to t is I. So the first derivative of this is actually identified as 3I e to the power of it. Okay, so this is the derivative we're going to use here as well. So we now have the z of t. We now have our z prime of t. What we need to do here is identify is a and b. A and b corresponds to the I forgot to say it corresponds to the boundary of your t. But since it's a circular path, obviously it starts with 0 and it ends with 2 pi because it's a circular path. It needs to be completely circular before we can identify the it to be a circular path. If it's not until 2 pi, then of course automatically our result here is no longer a circular path. That would mean our a is 0 and b is 2 pi. So we have this now as part of our intended target. Now, let me look closer to the given function, because some of us might automatically say, this being our z of t, I'm going to substitute that there. Obviously, for this given, our given function z is just z itself, so you can automatically substitute that, because if we're going to have here f of z of t, the parameter, it's still z of t, the parameter itself, as we change the z into that. But sometimes, if our given function is z squared, so it's not all the time true to substitute that there, okay? You could, of course, you need to really look into what is given. In this case, our given function is z, so it's okay. But for some cases, it might not be true. So with this now, let us now proceed, because all of the necessary items are given. So what we need to do now is to find now the integral rather of your f of z dz along the path, which is equivalent to, let me rewrite all of this again, f of z of t z prime of t dt from a to b. Substituting all the necessary information, the integral from 0 to 2 pi, and your f of z of t is just z of t itself, which is actually equivalent to 2 plus I plus 3 e to the power of it, the trinomial expression itself. So we'll have here 2 plus I plus 3 e to the power of it. Our first derivative is identified as 3I e to the power of it. This one here. then you have here dt. Now you can apply any method that you want. I would like to take this out because it's a factor that could stand as a constant. It doesn't have any t as a factor. So you have here 3i. Then I have here 0 to 2 pi of the same trinomial 2 plus I plus 3 e to the power of it times e to the power of it alone as I move 3i outside dt. Okay, so just simply apply all the process here. So by multiplication, you have 2 e to the power of it plus I e to the power of it plus, let's say here, 3. You add the exponents, right? E to the power of it plus it is 2 it dt. Okay, now using the linearity property, I still have 3i here. Don't forget about that linearity property that we discussed previously. The constants can be moved out to integral of 0 to 2 pi for your e to the power of it. Then plus I, the integral 0 to 2 pi e to the power of it. And you have here plus 3 integral 0 to 2 pi e to the power of 2it, dt. I might be using another page here later, so I'm gonna add if necessary. Now, before we continue, there is one thing I would like to emphasize here. Now, even without adding necessary constants for us to integrate the three integrals here, allow me to focus on this. Okay, I'm gonna put it here. The integral of e to the power of it dt starts from 0 to 2 pi. Okay, without adding or fixing it to be e to the u du. I would like to focus on the equivalent form of e to the power of it. As an Euler's formula, it's actually equivalent to cosine of t plus I sine of t, right? So if we're going to integrate that there, this is actually equivalent to the integral 0 to 2 pi of you have cosine t plus I sine t and then dt here. Okay? They're just the same. I'm going to use that because there are a lot of implications when we use the trigonometric functions for our range from 0 to 2 pi. Okay? This will be equivalent to 0 to 2 pi cosine t dt plus I. You can factor that. You have here sine t dt from 0 to 2 pi. Okay? What is the integral of cosine t? It's actually sine of t from 0 to 2 pi. Am I right? If you're not convinced with that, you can, of course, always check that. Okay? And the second one is you have plus I. The integral of sine t dt is actually equivalent to negative cosine t from 0 to 2 pi as well. Because if we're going to apply that, you have here sine of 2 pi minus sine 0. You have here minus I, as you try to multiply that, cosine of 2 pi. So since you're subtracting, how do we do this? We have, let us have minus, and then minus here, negative of I cosine of 0. What is sine of 2 pi? Sine of 2 pi is actually 0. Sine of 0 is also 0. Minus I, cosine of pi is 1. Plus I, cosine of 0 is also 1. That's actually equal to 0. 0 minus 0, this is also simplified 0. So what does this tell us? Okay, this specific expression, which is true for this here and that here, would just yield to 0 if we're going to transform e to the power of it into this form here. Considering that cosine and sine is actually the functions that would actually allow to simplify 0 and 2 pi. In short, this will just be equal to 0. Even if I'm going to move some terms here, I and I here, so that it will become e to the power of u du, okay, it will just complicate all the things. Because in the first place, the derivative of, or the integral of e to the power of it dt from 0 to 2 pi is 0 itself. So all of this in mind, allow me to add others, another page here. I'm gonna copy that. at another page, right? All of this here. Hopefully all of this are okay. Let me remove all of this. That would mean the form at the top, this would mean this is just 0. So 0 times 2 is of course 0. This is also 0. Okay? Now how about the remaining expression here? It's actually e to the power of 2it. So e to the power of 2it, the integral of that, 0 to 2 pi. Then we have here dt. Similar thing, okay? If I'm going to have, again, I'm leaving that in the meantime. If we have here 2 e to the power of 2it, using that form, we have cosine of 2t, because this can be written as e to the power of I times 2t, right? So plus I sine of 2t, okay? So if this is to be returned here, that's actually the integral of 0 to 2 pi of cosine 2t plus I sine 2t dt, which would be 0 to 2 pi cosine 2t dt plus I integral of 0 to 2 pi sine of 2t dt. So the integral of that, again, the integral of cosine 2t, if we're going to have it cosine u du, so you have here 1/2. Okay, so you have here 0 to 2 pi cosine 2t 2 dt, right? Plus I times 1/2. Similar thing, 0 to 2 pi sine of 2t 2 dt, so that we could actually integrate that, unlike the previous one, where it's just simply cosine t, okay, and then sine t. But the angle here now is 2t, or 2t, so that we have 2 dt. Anyway, you have here 1/2, and then you have the integral of cosine 2t is actually sine 2t from 0 to 2 pi plus I over 2. So the integral of sine 2t is negative cosine 2t from 0 to 2 pi as well. You would see that it's similar thing, 1/2. You will have here sine of 2 pi minus 1/2 sine of, 2 times 2 pi is 4, right? 4 pi. So 2 times 0 is also 0. Minus, plus, let's have it here, I over 2 negative cosine of 4 pi. Then you have minus I over 2 negative cosine of 0. Sine of 4 pi, second revolution, is still equivalent to 0. Minus 1/2 sine of 0 is 0. Plus I over 2 negative cosine of 4 pi is 1. You have your minus I over 2 negative cosine of 0 is 1. This is 0. 0 minus I over 2 plus I over 2 would still be equivalent to 0. In short, this entire form is also equal to 0. This is also equal to 0. So whatever would be the value of 3 times that, it's still 0. So what we have here, returning to the previous page, is actually having the form here of 3i times 0 plus 0 plus 0, which would give us 3i times 0 yielding 0. Now, surprisingly, the integral of the given function f of z equal to z around the circle centered at 2 plus I with radius of 3 is 0 after all of these processes. We use the parameterization of our circular path centered at not at the origin with radius of 3. And we have here all of the strategies that we have applied to. Of course, you can, as mentioned, you can continue doing that, but it will give you a lot of equivalent forms. Instead, we use this form here so that we can introduce cosine and sine that will actually use or take care of the 0 and 2 pi boundary easily because cosine and sine are trigonometric functions, which gives us again this to be 0. So 0 times 2 is 0. This is also 0. In the next page, this was also 0. So all of them are 0, providing us with this 0. Okay, this is the answer for this item. Thank you very much for watching.